Take a look at this map. This is the standard view of the world most of us grew up with, printed in our textbooks and hanging behind classroom desks. If you look closely at the top, Greenland appears massive. On paper, it looks roughly the exact same size as the entire continent of Africa, but the math tells a completely different story. In reality, Africa is roughly 14 times larger than Greenland. The images we trusted completely to teach us the shape of our world carry massive, calculated distortions about its actual physical dimensions. The root of this problem is pure geometry. We live on a three-dimensional sphere, but we navigate using flat paper and two-dimensional screens. If you try to peel the surface off a perfect sphere and force it to lie completely flat on a table, the material has nowhere to go. It will inevitably wrinkle, stretch, or tear apart. To get that flat image, cartographers have to choose what to sacrifice. They can accurately preserve size, shape, distance, or direction, but it is mathematically impossible to keep all four. Map-making is essentially the science of deciding exactly which geometric reality to throw away. This photograph shows the Roman ruins of Alexandria, the city where ancient scholars first tried to solve this exact problem. Around 150 AD, the Greek scholar Claudius Ptolemy laid a mathematical grid over the Earth. By dividing the globe into degrees of latitude and longitude, maps shifted from artistic guesses to precise calculations. Centuries later, as sailors crossed oceans in the 1500s, they ran into a deadly issue. On a curved Earth, the shortest route between 2 points is a curve, which is incredibly difficult to plot using a straight compass heading on flat paper. This is the 1569 Mercator projection. He engineered it so sailors could draw straight lines and follow a single compass bearing, but this required massive distortion. Everything near the poles was heavily stretched, expanding land masses far beyond their actual size. The Mercator map works flawlessly as a tool for sea navigation. It just completely sacrifices true visual proportions to make that happen. By the 20th century, cartographers wanted maps that prioritize the actual physical size of the continents instead of warped navigation routes. Introduced in 1925, the good Homolocene projection corrected size distortions by slicing directly into the map. It peels the globe like an orange and lays the Rhine flat. Landmass dimensions are accurate, but it creates severe, unnatural gaps in the oceans. In the 1940s, architect Buckminster Fuller created the Dymaxion map. He projected the globe onto connected triangles to minimize the obvious visual stretching. Later, the Gall-Peters projection managed to flawlessly display the true area of continents like Africa without slicing the map apart. However, it forced the land masses to stretch heavily along the vertical axis. Every time cartographers adjusted the math to fix the area of the land, they ended up distorting the recognizable shapes of the countries or breaking the continuous flow of the oceans. In 1999, Japanese architect Hajime Narakawa introduced what might be the ultimate compromise, the orthograph projection. It works by dividing the globe into 96 distinct regions, turning them into tiny triangles, and meticulously rearranging them into a neat two-dimensional rectangle. This method distributes the distortions so evenly that it's barely noticeable. Yet, even with modern computational power, the orthograph is just highly efficient at hiding the errors. The underlying mathematical constraint remains unbroken. Every flat map in history is mathematically incorrect. But those distortions are deliberate features, engineered to solve specific human problems, whether that's crossing an ocean or accurately comparing the scale of 2 continents. This photograph shows the Erdapfel, created by Martin Beheim in 1492. As a physical sphere, it is the oldest surviving globe, and therefore the only mathematically flawless way to represent our planet's geometry. But there is a catch. If you look closely at the oceans, you will notice an enormous missing piece, the Americas. Beheim constructed this precise, mathematically perfect globe just before Christopher Columbus returned from his voyage. A map is never a completely objective mirror of reality. It is entirely limited by the geometry we select and the boundaries of the world we currently know.